Hello again, guys. يعطيكم العافية. It's Mahmoud again. In this lecture, we will be continuing the work we started in lecture 6 about improper integrals. So we talked about the different types of improper integrals, type 1 and type 2, and their uses. And we talked about the odd and even functions and how to evaluate the improper integrals or any integral on a symmetric domain of integration. And we talked about the P integral and its importance. So in this lecture, we will be talking more about analysis of function behavior and the convergence and divergence of the improper integral. So you might have heard or someone spoke about in front of you that some functions are slow and some functions are fast. Okay, so actually not. Actually, there are some functions that evaluates more rapidly than other functions. So for example, if I'm comparing x and I'm comparing e power x, so you see x starts at 1, so this would be e, already greater than. However, at 2, this will be e squared. So it started with 2.7, now it's 5 point something. Now at 3, it will be e power 3. So you see, it's evaluating faster and faster. So when I reach 10, e power 10 will be a very large number compared to 10. So if I want to compare the two functions f of x equal x and g of x equal e of x, I would say that f of x is slower than g of x and g of x is faster than f of x. Why? Because here my reference is the speed to reach infinity, to evaluate to infinity. So this is what's meant by a function speed, and this is how we compare functions. In general, we have an axis for this, the rate of growth of these functions to infinity. And this axis starts by the ln x. So I can say that ln x is the slower function I know. Of course, the constant function does not even move, so it's the slower function. But from the functions that change variables, the ln of x is slower. Then comes x power p, then e power x, then x factorial, then k power x, then x power x. So x power x is the fastest we know. Okay, again, and combinations of x power x. So here, compare ln 2 to 2 power 2. See, this is 0.6 something, I guess, and this is already 4. Right? So if I have ln 3 and then it will be compared to 27. So this is 1 point something and compared to 27. So you see, we've already started evaluating terms now, 1, 2, and already the difference is very big. So yes, this axis is to be memorized. It's very important because we will use it in a main test called the direct comparison test. So we've discussed before that an improper integral could converge and could diverge depending on the behavior of this function. I can guess the area if the function tends to 0 and the curve of this function comes very, very, very close to 0, we said that the area could be constant, could be finite, and hence the limit, and hence the integral could be convergent. And we said that sometimes it doesn't come very close, or it doesn't come close at all. So the area would be infinity, and in this case, the integral could be divergent. So to start with, we'll start with the nth term test or the divergence test. The divergence test is as follows. if we have an improper integral f of x dx, it's enough for me to know the limit of f of x to know whether this function converges or diverges. Mainly, if the limit is not equal to 0, then this function diverges. Why? Because, as we've discussed before, that if the limit is equal to 0, this means that the curve is coming close. I don't know how close to the x-axis. So that's why if it's equal to 0, it's not necessarily convergent, as we've seen in the case of 1 over x and 1 over x squared. However, sometimes if the limit evaluates to be a constant, for example, or plus infinity or minus infinity, this means that the infinite block, the infinite rectangle I'm adding to the sum to evaluate the integral is infinity. So I added infinite areas of rectangles, and hence my integral should be divergent, right? So yes, if the limit of f of x is not equal to 0, or could be written this way. Let this limit be whatever it wants. It could be plus minus infinity. It could be some constant. Okay. However, it may not exist at all, the limit. So if my function is minus 1 power x, the limit as x tends to infinity would be minus 1 or plus 1. So the limit would not exist even. So in this case, my improper integral is divergent. I repeat, if the limit of f of x is equal to 0, then this integral is not necessarily divergent, or it's not necessarily convergent. We say that divergence test fails, or the divergence test is inconclusive. To move on to the power axis, or the growth of function axis we've discussed before. Why is this important? This is important because if I have two functions, okay, and one function is smaller than the other function, and suppose we have here 1 infinity of f of x dx. I can't know if this improper integral is convergent or divergent. I can't evaluate, and I couldn't find the limit of f of x. So what shall I do? What I should do is try to find another function g of x based on my intuitions. So I would guess if this function is convergent or divergent, and based on this intuition or this assumption, I will try to find another function, f of x or g of x, that is smaller than or greater than my initial function, based on this test. It's called the direct comparison test. So if I have two integrals, so we know that if f of x is less than g of x, then also the integrals of f of x is less than the integral of g of x, in case both are continuous, and we can't integrate unless the functions are continuous. So if we have f of x is divergent, this means that it could be equal to plus or minus infinity. This means that integral g of x is greater than something that is already very big, is infinity, and hence it's divergent, and vice versa. So if g of x is equal to some constant, right, and my function is already less than this function, so this of course is equal to some constant, and hence conversion. What I need to focus about is the intuition, how to know if I need to find a function that is less than or greater than. We will need the concept of slow and fast functions. So mainly if I have fractions, if I have a function f of x that is a rational function divided into g of x and h of x, if this function is made of a slower function over a faster function, so assume ln x over ex, then my intuition would be that the integral of this function will be convergent. My intuition, Okay, focus on the fact that it's only an assumption. I can't prove using my intuition. So if it's slow over fast, so the integral might be convergent, most likely will be convergent. And this way, I will try to find some function g of x that is greater than my function f of x. And g of x better be a convergent function, I know. Okay. For example, it could be the p integral discussed before. Or in other cases, if my function is made of a fast function in the numerator and a slower function in the denominator, this means that my integral is most likely to be divergent. So I better find a function g of x that is less than my function f of x. Less than, I didn't write this correct. Okay, so is less than my initial function. And this way, f of x and g of x better be divergent, then the function f of x is greater than a divergent function. And this way, I can use the direct comparison test to guess the behavior of my improper integral. So this is all about the direct comparison test. We need to focus on how to know what function I need to compare my initial function to, and the concept behind this test. So another function, another test that is very important is the limit comparison test. The limit comparison test, so if I have an integral f of x dx, and I couldn't solve it using the direct comparison test, I couldn't solve it using through the nth term test, it's not a p integral, I can say that if I could find another function g of x, okay, a function that I know its behavior, I know that it is convergent or divergent, and if the limit of f of x over g of x is equal to some constant, right? Some constant, then I can say that f of x and g of x both have the same behavior. Okay. The proof of this test is a bit complex. I will not go through it. However, you need to know that g of x is of our choice. We choose it the same as in the direct comparison test DCT. And this constant better not be 0 or infinity, because in case the limit was 0, it will cause a trouble, and in case the limit was infinity, it will cause a trouble. So if the limit of f of x over g of x is equal to a constant, then the two integrals f of x and g of x have the same behavior, behave alike. We have exceptions for infinity and 0. I can choose a g of x that is, I think here those statements should be reversed. Okay, so in case limit of f of x over g of x is equal to 0, then both integrals converge. So I need to find a convergent integral g of x. And in case, so this should be 0 and this should be plus minus infinity. And in case it's equal to infinity, then that function g of x I chose must be a divergent function. Right. So I think that's it for today. I will attach some exercises for you to solve, and I hope you study well and you benefit from this lecture. Thank you. Have a nice day.